So far in this unit, we've used the terms conductors and insulators a bit. Conductors meaning things that allow electrons or allow charges to flow, and insulators being things that don't allow electrons to flow. But really it isn't quite so black and white as this. It's more of a sliding scale than a binary switch. So for example, we might normally call air a pretty good insulator, but we know that given enough charge, we can have electrical currents jumping through the air. Something like a static shock can jump through the air. When you scuff your feet on the light switch or on the carpet and then touch the light switch, you don't actually have to touch the light switch. You can get some arcing across the air. Or a bigger example of this would be lightning striking. That's going through the air as well. So instead, we need to talk about this in a little more detail using the terms resistivity and resistance, and how those define not just whether an electron can flow through this object or through this material, but how well it can flow through. Let's think of this image as representing, say, a wire, and we're going to have electrons trying to flow through this wire. Now, we use the term flow, and I think we bring up a picture of something like water going through a pipe, but it's not really the same thing here. Because the pipe we think of as being empty. It's got air in it, but the water can flow pretty freely through that pipe. But electrons aren't going through empty space. They're going from atom to atom. Each atom has electrons around it, and the electrons are jumping from atom to atom. So if we follow an electron here, maybe it starts over on this atom, and then we could have it jumping across to this one, and then we could have a jump over to this one, and a jump over to this one. And so we can think about a few things that would make this electron have an easier time. If the atoms are pretty close together, that gives the atom or the electron a pretty easy time flowing. If they're regularly spaced, that does it as well. So, for example, we've got a pretty small jump here, but then the next jump is a pretty big one in either direction. And so, maybe we have to build up a little more excess charge on the left side of the diagram here before we're able to make that jump. And then, another pretty big jump here, but then a fairly small one to get over to this atom. We also have lots of different paths here. So we might have another atom that we're watching here. Maybe it jumps down this way to begin with, and then kind of over this way. And they can go backward too. Maybe it goes over this direction and then back this way. And so how those atoms are arranged makes a big difference in terms of how easily the electron can flow through this material. Here we're looking at two different wires. They're intended to be made of the same material, which would mean the dot spacing would be about the same, or the atom arrangements would be about the same. And if we looked at electrons in this top wire, the wider wire, we see there's lots of different paths for the electrons to follow. So we might have one that goes all the way across at the top, we might have one that goes all the way across in the middle, one that goes all the way across at the bottom here, and then we can have some crossing over here as well. So what we see is that this wider path, we have lots of different options for the electrons to follow. But on the bottom one, we have a pretty small number of paths that this electron can follow, just because there aren't as many atoms, or there isn't as much area through which it can travel. There's really only one alternate to this. We could have go down to this one first and then follow the same path. And so we get kind of a traffic jam here. The electrons can't move into an area where there's lots of electrons there already because they get repelled by like charges. So they kind of have to wait for the other electrons to make their way through. So the traffic jam analogy is kind of a nice one here, where this would be like a freeway with lots of open lanes, and this is a small 2-lane highway. And so we try and get too many cars going through on this 2-lane highway, and we get traffic backing up really far. But up here we can get a lot of cars, or in this case a lot of electrons, moving through that space because there's a lot of paths that they can take. Now these two wires are the same material again, going from the same 2 points from the left side of the picture to the right side of the picture. And the only real difference between these is the length of the wire. So if we followed an electron here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atom jumps to get to from the left to the right side here. But if we watch this one, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 jumps to get to the same place. Now, it's not really going the same route here, so we can understand it's tougher because it has to travel farther to get to the same place. So the length of this wire, that's going to impact how well the electrons flow through this object as well. So now we come to the big idea here. Resistivity and resistance are both ways to describe how well current can flow, or how much of a fight this material or this object puts up against electrons jumping through it. Resistivity will refer to a material, like, say, copper. Copper has a very low resistivity, which means if you make some object out of copper, like a wire, then that's going to have electrons flowing through it better than if you made the same object out of something like, say, brass. Brass has a higher value for resistivity. On the other hand, resistance is looking at, for a specific object, how difficult is it for electrons to flow through this thing. And so that's going to depend in part on what we make the object out of. So do we make it out of copper or do we make it out of brass? But the other piece here is the shape of the object. How wide is it? So like how many lanes of traffic do we have? And how long is it? Do we have a really, really long wire or a really short wire? That will impact how well electrons flow through this object, how easily they can get from one side to the other. And so we come to this equation, which is on your AP Physics 1 equation sheet. R equals rho L over A, where R is the resistance in ohms. And in ohms, we use the Greek letter omega. It's the upside-down horseshoe-looking thing here to represent this. So ohms for resistance. And then rho, which is the resistivity of the material. So if we were using copper, we'd have one value for resistivity. If we were using brass or gold, then we'd have a different value for resistivity. That's going to be measured in ohm meters. Now, why the meters? Well, that's to cancel out with the other measurements that we have here. We've got L, which is the length of our component, or the distance from one side to the other, from one end to the other, measured in meters. And we've got A, which is the cross-sectional area of this component. So not just how wide it is, like how many lanes it is, but we can work in 3 dimensions here. So the whole cross-sectional area, if it's a circular-shaped wire, then we use pi r squared if we know the radius to find the cross-sectional area. And that's going to be in square meters. So when we do the units here, we've got ohms times meters again here gives us ohms meters squared. Then divided by area in square meters gets us just ohms, the resistance.